Hi everybody, I'm Kyuzo and welcome to this introduction to format string exploitation video for the FuzzySecurity website created and maintained by a colleague and friend of mine, Beef, as you probably know already. Quite a few months ago, Beef and myself, we were working on a exploitation workshop. He was dealing with the Windows part and I was dealing with the Linux part, and I had promised him to make some exploitation video about Linux or some exploitation tutorials about Linux, and this is my attempt now after a few months. I chose to focus on format string exploitation because I think it's been quite important in the last, say, couple of years as far as Linux is concerned. We've had major mainstream distributions like Fedora, OpenSUSE, Ubuntu, all shipping at some point with some program vulnerable to format string exploitation. Just a very quick example, the sudo format string vulnerability that was back in 2012, and it was quite big and allowed privilege escalation, and Fedora 16, which is the distribution I'm using to make this video, by the way, was vulnerable to it. OpenSUSE had the vulnerable version. Also, some time before that we had Exim, the Exim mail server. Then we had Pidgin, the instant messaging program. A couple of years ago we had quite a big one in CAPS, the printing system for Unix. The LP password had a format string vulnerability, and that was exploitable. And there was a very famous and interesting article on Frac written about this format string exploitation. So it's interesting, not very well known, and hopefully you will learn something useful. I won't say much about what a format string is. We will just take a very quick look at the main page for format strings, and well, basically, as you can see, we've got a family of NCC functions called the format string family of functions, or the format family of functions. These are printf, fprintf, sprintf, and there are many others actually. Now, these functions are basically used to convert primitive values of the C language, things like integers, doubles, strings, to convert these values and to present them on the screen with a particular formatting that the developer has chosen. Now, these functions take a variable number of arguments. We can see, for example, printf that takes this ... here actually again tells that this takes a variable number of arguments, and one of these arguments is the format string, the so-called format string. Now, format string contains normal characters that are just print in the output as they are, and then it contains some placeholders that actually specify how the next argument needs to be formatted in the output. So they actually contain format specifiers that say the next argument, well, treat it as a signed integer, for example. The next argument, well, that's a string, so print it as a string. Let's take a very quick look at example.c, which is a format string example of how format strings are used. So we can see here we've got A, B, and C, three variables. One is an integer, then we've got a floating point variable, and then we've got finally a string. And here you can see printf, and we are passing A, B, C, so we are actually printing A, B, and C. And as you can see in the format string, we've got standard normal ASCII character, C equals, comma, and stuff like that. And then we've got the so-called placeholders, which contain the conversion specifiers. So for example, percent is the key, the meta character that starts a placeholder, and then we've got a conversion specifier, which is a letter. In this case, D stands for digit or signed integer, F stands for floating point value, S stands for string. And each of these, of course, it's telling the function, when you get here, fetch the next argument of the stack, which is an A, and treat it as a signed integer. Then fetch the next argument of the stack and treat it as a floating point value, and so on. If we execute this program, as you can see, this is our expected output. The placeholders have been replaced by the actual content of the variables, and they have been formatted or rendered in the correct way. Now let's try to change something here. So if I tell printf, instead of %d, if I say %u, which stands for unsigned, and I recompile this application and run it again, as you can see now we don't have -5, but we've got this value. Now this is the same value, the same variable, same 32 bits, but we're just telling printf to interpret it in a different way. So this should make very clear what printf is actually doing with these values. The one thing that I want to add is that with these placeholders we can specify a width field parameter. So for example, I can say 20u. This means, as you can see here, I have to recompile it a moment. Okay, this means, as you can see here, that we are adding some kind of padding, so that this argument here just takes this much space when we're printing it, and this can be done with every argument. And I'm mentioning it here because it's really very useful when we want to do a format string exploit, because as you can see, this allows us to actually control how much data we are writing. I will repeat it because that's a very important concept. This this value here, this width value, allows us to control how much we're writing. If I change this to 40, now I'm adding 20 bytes to the count of characters I'm writing. So this allows me to control very precisely what happens. And the second point that's important before we go on is that each of these placeholders in the format string actually tells printf, okay printf, go off the stack, take the next argument. Now, where is the vulnerability here? In this case, there is no vulnerability because the format string, as you can see, it's a constant value. Once you compile the program, it cannot be changed. You can change the content of these variables, but the actual format string cannot be changed. Let's take a look at fmt.c. Now, this is a vulnerable program. Why is it vulnerable? Well, first of all, this contains, just in case you want to have fun, this contains a buffer overflow vulnerability, but we're not concerned with it at this moment. What this does, and what we are actually interested in, is that this takes an argument, a command line argument, copies it into a local buffer on the stack, and then it prints it or echoes it back to the user with printf. So if I run this command, fmt hello, it's telling hello. So apparently this is working correctly. However, look at this printf. This doesn't look right. What this should be like, what this should look like, is something like this. Format string %s. So this argument, which is user input, should be rendered like this, %s and b. However, the programmer is lazy here, and so they're just writing printfp, because you know what, it works just fine, right? We've seen it before, we've run it, it works fine. It echoes this thing here, the user input. However, as you can see here, now this user control argument has actually become the actual format string, and this is where the vulnerability is, because now the user can, or the attacker, the malicious user, can provide a input that contains those placeholders or format specifiers, and thus modify the behavior of printf and making it do things that it was not supposed to do. And let's take a look at this. So instead of saying hello, I'm going to say AAA, which is okay, and then I'm going to say, I'm just adding some data here so that we can then recognize this data when we see it. Now I say %x. Now x means print the next value of the stack as an hexadecimal value. I could have said %d, but %x is probably easier to it makes it easy for us to identify the values we see. I execute these, and as you can see now, instead of seeing %x, I see a value. Where is this coming from? Also this value here. And look at this, 41, 41, 41, 41. Well, this looks kind of familiar, AAA, right? That's our input. So if I add %x here now, what do we expect? 42, 42, 42, right? So what's happening here? Let's go a second into the debugger, which is probably gonna help us understand this much better. So we're using GDB here. GDB is the standard debugger for Linux systems. If you've never used it, it's quite simple. Let's disassemble the main function here a moment. Let's take the call to printf, which is here, and set a breakpoint by saying b star and then the address where we want to set our breakpoint at. So now we can try and run it, and again we are going to pass our input here. We run it, we hit the breakpoint. So what we want to do now, let's take a look at what the stack looks like before the printf function is executed. So we're going to use x, which stands for examine, and then we're going to say 20 words of the stack as hexadecimal values. So basically we're dumping the content of the stack from ESP, that of course points to the top of the stack that is here. Let's take a look. So this is what the stack looks like. We can see our input that, as you remember, was copied onto the stack. Makes sense, in a local buffer, and some other values around here. Let's continue, and here it is, the output of printf. And as you can see, what printf has done, well, it's reached this %x and it said, well, okay, so it means that there was an argument for me. I need to go and fetch it off the stack and print it as a hexadecimal value, and this is actually this value here of the stack. Then he went and fetched the next one, which was a 1, and it's printed here, and so on and so on. So it's got this value here, and as we can see, it's here, and then all the other values that we control. So let me make another important point here. We control these values. This is our input, and this is going to become quite important later when we try to actually exploit this. Before going on, I want to introduce another concept that's gonna help us in writing an exploit using format strings. I'm gonna kill this a second. I'm gonna get out. So AAA BBB %x like this, and 41, 41, 41, 41, 42, 42, and so on. These are the values we are interested in, and as you can see, this is the fourth value that we can fetch off the stack from printf, and this is the fifth value, like this. There is a way to directly access these values without having to go through each of the preceding values, and this is called direct parameter access. Now, what we can do with direct parameter access, we can actually say %for $x, which means just go and directly fetch the fourth parameter, which in this case it's going to be 41, 41. For this to work, we need to add a backslash before $, because that's a shell meta character and we want to escape it. As you can see, we've actually directly accessed one parameter. So at this point, if I say %5 $x, that's gonna access 42, 42, 42, and I could, if I wanted, I could just fetch any argument off the stack. I can go on and take the 8th value and so on. And this is what basically direct parameter access is, and it's gonna make our life easier. Okay, so let's try to recap what we've seen so far. We looked at what a format string is in general, how they are used in the program to convert and represent values on the screen, and they can actually be used to write to a file. For example, log functions make use of format strings. They can be used in many other scenarios. We've looked at what format specifiers are, and we've looked at the correct way of using a format string, which is by passing a constant format string as the first argument to printf, and then the list of the other arguments. And we've seen the wrong way of using format strings, where we allow the user to control the whole format string or parts of it. In our example, again, I'm gonna bring it up again. In our example, this is user input and we are just passing it to printf, and this is not the right way of doing it. The right way would have been to add a first argument as a constant format string with %s and then adding these arguments later. Now, the fact that we can control the format string basically means that we can make the printf function go farther down the stack than it was supposed to go, and read the content of the stack. Now, by itself, this is a information leakage, so we can access memory we were not supposed to access in the first place. However, if we couple this with another vulnerability, say for example, say a buffer overflow. So we've got a buffer overflow vulnerability, but we cannot exploit it because the compiler has put there a canary between our buffer that we can overflow and the return address or the frame pointer, whatever you wanna overwrite. However, if there is a format string, what we can do, we can first leak the canary value, so then we can use it to build our attack string dynamically, so that we can repair the canary and exploit the buffer overflow. So information leakage is quite bad. However, in the second part of this tutorial, we will look at something else that format strings offer, a really weird feature that will allow us to actually get control over the program just with a simple format string.